For e-learning today, I am postponing our quiz for 6-1 to 6-3 until Friday, and then we are going to go through Lesson 6-4 here, and the assignment for Lesson 6-4 will be due next Tuesday. There is a review assignment for getting ready for quiz 6-1 to 6-3 posted on my webpage that you should complete for Friday. There are 11 problems. And then the assignment that I give you after this lesson will be due on next Tuesday, the 22nd. And it's posted on my webpage. So Lesson 6-4 is about roots of real numbers. And we are going to be simplifying radicals in this lesson. To give you some background, let's start with square roots. For any real number a and b, if a squared equals b, then a is a square root of b. For example, we know 3 squared equals 9. We also know the quantity -3 squared equals 9, which means both 3 and -3 would be square roots of 9. Then you see the definition of the nth root. It says for any real numbers a and b and any positive integer n, if a to the n equals b, then a is an nth root of b. For example, we know 2 to the 5th equals 32, which means the 5th root of 32, the 5 in the crook of the radical is the root, so the 5th root of 32 would equal 2. We also know the quantity -2 raised to the 5th equals -32, which means the 5th root of -32 would be -2. I want you to make the connection between two forms. It's a little hard to read on that handout, so I have it enlarged here. For real nth roots, we have two notations that we work with. We have radical notation and we have rational exponent notation. And in lessons to come, we'll be using this quite a bit. But what you see here is the nth root of b. The n in the crook of the radical is called the index, and the power that the base is raised to is an implied 1. So the nth root of b is equal to b raised to the 1 over n. The numerator of that rational exponent, this is rational exponent notation, the numerator is the power that b is raised to in the radical notation. The denominator of that rational exponent is the index. So the nth root of b is equivalent to b raised to the 1 over n. Likewise, if you have the nth root of b to the m power, that is equivalent to saying b raised to the m over n. This form is really important because it helps us in simplifying roots where we have an index and a power, because the power that the base is raised to gets divided by the index, which is n. For instance, the cube root of x to the 6th would be x to the 6 over 3, and since 6 divided by 3 is 2, that would become x squared. That's what we mean when we see these notations. And so going back to the original handout, if you look here, depending on whether the index is an odd number or an even number, and whether the radicand, the quantity under the radical, is positive or negative, you have different outcomes. So when n is odd, that's numbers 1 and 2, that means you're taking an odd root. If the radicand is positive, like the 5th root of 32, the root is positive and there's one positive root. In the case that you have an odd root and the radicand is negative, like the fifth root of negative 32, that means the root is negative and you get a negative 2. How about when the root is even? Well, when the index is even, like in a square root or a fifth root, when it's even, if the radicand is positive, there are going to be 2 roots, one positive, one negative, for instance, the square root of 9. If you want both roots, you're going to have to put plus or minus square root of 9, which means the roots are both positive and negative 3. Typically, when you see the square root of 9, we only want the positive or principal root, which is positive 3. And when we're taking the negative root, that's how you get negative 3. So the opposite of the square root of 9 is negative 3. If you try to take an even root of a negative radicand, like the square root of negative 9, that's not going to be real. So there is no real answer. There's an FYI here that I'll explain, but we'll get into a little more detail next week. But this says when the index is even, you're taking an even root, like a square root or a fourth root, of an even power, and it results in an odd power, then you have to insert absolute value bars to ensure that the result is non-negative. So for example, right here, I am taking an even root, a square root, of an even power, x squared, and that results in an odd power because the power 2 divided by the index 2 is 1. That's an odd power. That means I have to insert absolute value bars. Why is that necessary? Well, if the value of x was negative 3 here in this problem, negative 3 squared is a positive 9, and what's implied is the principal root, or a positive 3. But we're saying x is really negative 3, so to ensure we get the right root, we insert absolute value bars. You don't really have to worry about it a lot here. Try to insert them if you understand where, and don't get hung up on it because later in the chapter they're going to say assume non-negatives, and it will become something that we don't have to worry about so much. So let's look at some problems here. I'm going to move this up a little so you can see better, and this handout can be downloaded from my web page. But this first problem says, what is the cube root of negative 343? And this handout will also be on my web page, but you are going to need to learn your perfect squares, perfect cubes, perfect fourths, perfect fifths. Most of you should already know your perfect squares, at least to 10. I'd like you to learn down to 15. For perfect cubes, down to 7 cubed. For perfect fourths, down to 5 to the fourth. For perfect fifths, down to 3 to the fifth. So these are useful because it's going to save you a little time if you can learn them. And a lot of you already know several of these, just maybe not all of them. So when we see the problem, which is the cube root of negative 343, we have to understand that 343 is a perfect cube, and if it's a perfect cube, our calculator actually can help us find that. And in this case, because the root is odd, we get an odd result, which is negative 7. Look at number 2. The square root, which we're comfortable with, of 144 p to the 6th, the square root of 144, of course, is 12. It's the positive root because we don't have a minus in front of the radical. And then 6 divided by the index of 2, the power 6 divided by 2 is 3, so that gives us p to the 3rd. You might be wondering about the absolute value bars. Here's a perfect example of where to insert them around that term, and that's because I took an even root, a square root, of an even power 6, which resulted in an odd power, That's where you want to insert those absolute value bars. And again, do the best you can with that, but don't get hung up over it. Number 3, plus or minus square root of 4a to the 10th. Well, we have plus or minus because they want both roots. We know the square root of 4 is 2. The square root of a to the 10th, we're going to take the index of 2, which is implied, and we're going to take the power of 10 and divide the 10 by the 2, and that's how we get a to the 5th. And so we insert absolute value bars, again, because we took an even root, a square root, of an even power, 10, which resulted in an odd power. Moving down, you can see in the next problem, we have it's hard to see here for me, we have a 5th root of 243 p to the 15th. Again, as you learn these powers, we're going to learn that the 5th root of 243 is 3. So what we have here is 3, and then the variable p raised to the 3rd, because 15 divided by 5 is 3. And you should be able to look at each of these examples and see what's happening. You are taking the coefficient and using the perfect roots to simplify it. They will all be perfect nth roots. And then for the variable factors, you want to take the exponent and divide it by the index. And in any instance that you take an even root of an even power that results in an odd power, you want to insert absolute value bars. In number 12, that's exactly what's happening. You're taking a square root of the quantity 3x minus 1 squared, which is an even power, and it results in an odd power because 2 divided by 2 is 1. So we insert the absolute value bars. Also, as you look at 14 and 15, you cannot take roots of individual terms in polynomials. What you need to do is factor, and in both 14 and 15, they are perfect square trinomials, and they can be rewritten as the square of a binomial. In 14, the quantity x plus 5 squared, and in 15, the quantity 6x minus 1 squared. And when you take the square root, which is what we're doing in both problems, you're taking an even root of an even power, which results in an odd power, 1, so we insert the absolute value bars. We didn't need to do that on number 13 because it was an odd root, and so with odd index, you don't have to worry about absolute value bars because results are either positive or negative. The last thing you need to do in this lesson is learn how to use your calculator to find roots, and we'll go over that a little in class Friday next Tuesday, but explore your calculator and see if you can figure out how to find roots that are other than square roots. A lot of you that have graphing calculators, if you look under the math menu, you will see cube roots listed there. There's some other shortcuts I can show you, but do a little exploring on the internet to help you find how to take roots on your calculator. And we'll follow up with that on Friday and next Tuesday. All right, check the web page for your assignment. I hope that helps you, and this can be brought up as a sheet, as an attachment to look at as well.